Okay, so from that, from the uh, last session, we were reviewing these properties of the silicon, right? The ground state, right? And we checked this, we were able to check in with different functionals, basically with PVE and PVE solve. We were computing the equation of the states, and we compare, as you can see, with the other with the initial uh, functional, we use the LDA and we compare with experiments, okay? But now from now on, we are going to consider the PV, right? Why PV? Because it is from this, in this community, PV is very well used. So that's the reason why we are going to continue with PV, okay? So first thing is that you have to learn how to report the crystallographic information of this material. So that's the reason why I'm going to teach you how to do this, how to create this table, this information of this table that is here. So let's start with this, please. First of all, go to the file, the files, open the postcard file, please. You see here, and you're going to change this value here, right? You're going to change this value that is here, the optimal value that we computed, right? So the optimal value for PV was, what is this? Is this PV? So let me check. Let me check. If this is not. Just check the value that we computed in PV, the lattice parameter. It was this one, right? This one. Copy this and paste it here in the postcard file. Okay. So this is the value, the optimal lattice parameter from PV. We computed this, right, last week. So we're going to copy this, control this. And now save it. And now what we're going to do is in the terminal, see here, we open the terminal, and you can copy this command. So we're going to use hacer to transform that file. You see, we're going to transform that file with this, okay? Sorry. We're going to transform this file. Let's start again. This is the way that I'm going to create a zip file from the postcard file that we edited. I repeat again, please. The postcard file is this. Look this. This is the postcard file. So I just edited this value. As you can see here, I put this value. From where did I take this value? From this. From the optimal lattice parameter we compute for PVE. See? Once you have this, don't forget to save it. If you edit this, don't forget to save this postcard file. This one, save it. Close it, don't need anymore. And now we go and we do this command line in this, okay? So in do this, look this, we are going to we are going to have a file called post.zip, as you can see here. You can open here with this. You see, this is the structure of zip file. So please check this, please, everyone, till if you have this post.zip. Okay. Somebody need my help, please. You got this, please. Post. So you have to have this file, post.zip. The one here. Okay. Repeat again this. How you can the first thing you have to do is to edit this postcard file that is here, right? And after what you do is to have the number, the scaling factor in this case is related with lattice parameter of this value. Once you have this, you will be able to get this file post field. post.zero. Okay? Everyone until here, please. Angel, got it? If you have this, please do click in this. You see in the manual says we are going to do it called the find sim. The program in online it's called find sim. Just click over there. I'm going to open my browser. Here, this. I'm going to put it here. You see? What is this? Find sim. Repeat again. No, not it's not showing this. So it's like okay. If it's not fine, please. Sometimes it fail. I don't know why. So just put this find in the browser. Put find sim. Find sim. It is. It fails. Sometimes fails. So I put in the browser just this and then find sim. Of the hand. So you put this find sim, and you're going to have this find sim isotopy. Okay. Please open this. You're going to have this. Okay. And here it says import the data. So you're going to choose the data. So you say choose a file, and I'm going to browse here to the I'm going to browse here to the file that I created a moment ago. There is post.zip here one, you see, upload, and after that you put OK. That will give you you see, the information, the crystallographic information of my system. Look this. Here is space group is 227, is FD minus 3M, you see? And here you see the lattice parameter. You see, this is the one that you want to report. The lattice parameter of the unit cell. Because originally here is the lattice parameter of this primitive cell is this, but we are going to report of the unit cell. That is what we report in the literature. So basically, I'm going to share you the legal information that you have to report the stereo. So somebody, some experimentalist, for instance, some crystallographer will understand completely what you want to represent. Okay, so everyone till here, please. You have this data. We're able to get this data. I'm going to pause this for a moment. So as you can see from this data, I get this. Initially, this is information you fit in your system. In your system, the primitive cell has these lattice vectors, you know. This is the size of the lattice vectors and the angle. Okay. But later, after it appeared this, you know, save created by version and appear this information, this is the information of the unit cell of your system. You see, it has A, B, and C is the same. So it's a cubic system. It has 90 degrees, and this is optimal volume. Here's the symmetry operations here. And finally, here you have the position of the atoms. In this case, you have to provide only one coordinate because by symmetry you are going to get the next and so on. You can get all the information on of the structure. Okay, so what remains here is this, right? So I'm going to put this here. So I'm going to put this. I'm going to put the crystallographic information. So let's create this table, please. So here I show you the data that I just show you in a moment from the website. Look, this is space group is important and so. Therefore, you can see here you can get the information, right? So you can write down now the crystallographic information of your system, right? So this is the way. So we can create very quickly this, you know. So let's put this crystallographic information or the crystallographic data of silicon using PV. So this is the subsection of this. Okay. So let's put this. So we can do this. You know, this is I'm going to put a data table similar to this, right? So I'm going to start to create this very quickly. I'm going to show you how to create very quickly this, okay? So you can create the first of all is will be property and calculated. So it will be like this, property, comma, with PBE, GW, EAW, PBE, right? First entry. Next, I have the, what is the property, right? I have the property of a space group. And I have here, the space group is FD minus 3M 200. Sorry, FD 3. This is the minus, sorry, M. So this is the international tables. This will be the name of the abbreviation of the symmetry of the system, but also the international tables we also they know by the number 227 FD minus 3. Next is A equal to B, comma. Next is A is equal to B is equal to C. In what? This is in Armstrongs, right? What is the value? Is this value, right? So it's 5 on the one that we put it in Postcard file. 69. I'm going to put only three decimals, please. So let's put only three decimals. 69. We approximate this. Comma. What else? We have alpha, beta, gamma. So we'll be alpha, beta, equal to gamma. In what? In degrees. Degrees is like that. So we like here is the, right? It is 90 degrees. Comma. What else we have? We have a volume in Armstrong to the cube. Armstrong to the cube, right? We have what is the value, please? The value is from here. We're going to take this. We're going to take only with the volume with two decimals, please. So from here, Pierre, the value, where is the value? Here, 56. See? This is, I'm going to take from this information, the value, the volume. What else, comma? We have the bulk modulus, V sub 0. In what? In gigapascals. Gigapascals. Right? The bulk modulus we computed, it was around 89, right? What else? The V sub 0 prime is has no units, will be 4 point, around 4.3. That is the values that we computed, right? What else? The sides. U, V, and W. Comma. The sides is like this, right? So we will like this. Silicon 1, comma, and the sides here, please. You can copy and paste this. This is silicon one, you see, it is 0.25. There it is. That's it. Okay, so we have this, and that is my table, please. I'm going to put this. This is the table. Will be something like this. Ah, this is UV. Sorry, this is comma here. And there it is. Okay, so we have something like this. So this is the table that we can read. Anyways, I showed this table so you can transform this to LaTeX if you like. You can transform this to LaTeX. Text form. And you can copy this, right? So I'm going to copy this. Copy this. Paste it, for instance, in a LaTeX application, you can, any LaTeX application, you can copy this. Paste it. There it is, right? So we have this information. Okay, so this is just to show you how to create a table. Hopefully this, okay? So this is the way that we are going to report when you compute any structure. Please, we have to record the crystallographic information in this. Okay, so this is why, because for the crystallographers, this is very easy to read. You know, they understand very well. If you give this, you give the lattice parameters, the volume, okay, it's because you give the lattice, parameter, you can infer the volume, and this, the size. So this is the inequivalent position of the atoms. So you can generate by symmetry also the rest of the position. That's it. Okay. Questions in here, please. I'm going to pause here for a moment. If you have any question, please. Now we're going to start with the next section, please, is the silicon crystal ground state properties, okay? For that, we're going to use this part 5 silicon tree. So I'm going to expand this part 5 silicon tree. See, I have this data here, and we are going to follow, okay? What we are going to do? First of all, to get the ground state properties, we are going to compute. One of the properties we're going to try to predict is the cohesion energy. For that, we need the energy of the silicon atom isolated. Okay, so before we do that, as you can see, we're going to use, first of all, the postcard atom and incar st, and we're going to use this script atom.sh. Okay, so let's check this. Okay, so let's check what is this files. So you see, we're going to start with computing this, the energy of the isolated atom. For the reason we're going to use this, you see, Oscar atom here. And I put this 12 angstroms because 12 angstroms of the size of the box is enough. Remember that we already compute this, the size of the box, and we arrived at the conclusion is with, I remember it was something that 10 angstrom was enough, more than enough. That's the reason we are going to use this, okay? So to run this atom SH, you see, we need to, first of all, we're going to use incar st, but we need a postcard file and also a podcast file. Check the podcast file we're going to use is the podcast file PAWPVE. So we're going to use the what functional for my system PVE. So it will be GGA PVE. That's the reason we're going to check this. And in ST, as you can see, since we don't mention what kind of functional we're using, by default is the functional is mentioned in the podcast file. That will be a PVE, right? And look here, I put here is near zero. Okay. Now let's check the K points for the atom. You have to use only a gamma point, as you can see, one K point. Okay. So before we start, please, we have to edit. We have to name. Okay. So I'm going to do this. I'm going to this, look this, I'm going part 5, please. So the first thing that you have to do is to have the postcard, and key points. Here, I don't have a postcard, I have postcard atom, postcard. I have to do copy postcard atom to postcard. First thing is, I have postcard, yes. I have Incar ST, but Incar ST uh, in this script will transform to Incar, no problem. And finally, the key points. I need a key points. What key points? Key points atom. This one. So I'm going to copy these two key points. See? ULS, please. Now you have Incar. Well, just in case, Incar ST. Why? Because in this script, atom.sh, see, is using this Incar ST to the parallel part of the to use the parallel version of this VASP, and it's going to rename to Incar. Please, here you don't have to do this. I'm going to do myself only for my case. I'm going to put this only for me, please. You don't need to change this. Okay, I think I'm ready to run. Check this, please, again. If you like, ASIC U minus B, the postcard, to see what system we have. Look the system I have. I have this box of one silicon atom. The site is 12 functions, by the way. So I'll close this. I'm ready to run, right? So what I'm going to run, please, is the atom. So let's check again what is going to do the atom.sh. You see, it's going to run this, and after that, it's going to put this output atom.out, and it's going to give you information about the energy of my system in the file called atom.dat. So let's check this, okay? Let's run it, please. Okay. So I'm going to pause here. I'm going to pause for a minute. So after it finishes, please, have to have this file, the atom.dat. This file. The atom.dat. Okay. You have this. I'm going to open this in here. Atom.dat. This is the file. This is the value you have to have. Okay. I'm going to wait a little bit. So now we have this. The energy of an isolated atom is this. Okay. As I mentioned before, your result has to be exactly the same in this to the milli-electron volt precision. Okay. So now next is we're going to compute the total energy of the system, right? For the bulk, right? With PV. So we have to use these lattice parameters that we compute previously, right? Okay. So we are going to run this bulk.sh. We have to run this, okay? Look the file I need. I need Incar ST, okay? We have to check the Incar ST, and that's it. The rest, you see, after it finished, it's going to create the charge density, the outcome file, and OCK. So we are going to need this charge density, right? By the way. And after this, look this, we are going to compute this the band structure. So we have to check what is this K points BS. We don't have this. So we have to create this, okay? And that's it. So that's the reason why in this calculation, we are going to compute the ground state properties. And after this, we're going to compute the band structure here. See? So let's start to change things. First of all, I'm going to change, you don't have to change this, please. I'm going to do this one for my case. Nothing else. The rest is the same. Now let's go, please. First thing is you don't have to change anything, only myself. I'm just showing you what we are going to do. So the script is telling you what are the steps we are going to do and what kind of files we have to have ready. We have to have ready, as I mentioned before, we have to check what the Incar ST we are going to use. We have to, this will produce the first calculation. You know, there is here one calculation. If finished, it will create this bulk.dat with information of the total energy for the system. And after it also is going to create this chcar.vasp. So this is the charge density that we're going to visualize. And after we finish, it's going to copy this kpoints.bs. What is that kpoints.bs? We are going to create together, and it's going to remain to kpoints opt. And after, it's going to create a new increment with this kind of parameterization, and it's going to finally create some output files that we're going to see in a moment. Okay, so please don't change anything here. Open the incar st, please. The incar st here, you are going to put here this to -5. Look here, it is here. How it should look the incar file. You see? Is mere -5, so that is more appropriate for solids, so for condensed systems. I'm going to, please don't forget to comment I spin. You don't want to compute a spin polarization. If you compute with spin polarization, you're going to see that the results are basically the same, but you're going to spend twice the time. So don't do that. Also, L orbit, please uncomment and L orbit and comment L charge. Please. I'm going to pause here. I put the postcard file bulk with the optimal lattice parameter for PV, right? So this was the parameter we use in the PV, okay? So this is the optimal lattice parameter. You don't have to change anything. But remember, this is for the, if we compute the ground state properties, you have to remember the postcard file has to have the optimal lattice parameter. In this case was this value, right? And that's it. Control S, I didn't change anything, but you have to change, right? You have to copy the postcard file, right? Bulk to postcard, isn't it? What else? The K points, please. The K points, we're going to use the K points we know that converts the total energy. K points bulk will be this. So please copy the K points, CP, K points hyphen bulk to K points. Okay. Now what remains is to create the K points hyphen BS. Okay. To do that, look this, we're going to use the seek path. Okay. So before I continue, please, I'm going to pause here in a moment. So let's first of all let's check that you have the appropriate postcard file and it's fine. So you do it right. Seeking minus B postcard. You see, and you got the crystal. You see, that is the structure of my FCC with PV. So this is the optimal structure using PV. Okay. That's the reason. Always when you are going to run fast, please check what postcard file you're using with us. If you're not able to open with us, some problem has postcard file. Also check this K points, please. Has to be this, right? 9 and 9, you see? This is for a crystal. What else? Now we have to create the in the bulk SH is invoking this cap points hyphen VS. So we're going to create this cap points hyphen VS, please, because there is no here. So I'm going to teach you how to do it. I'm going to repeat as many times as you need. Please, to do that, go to this website called SeekPath. Open. See? This is SeekPath, please. And you're going to upload this postcard file. So upload the crystal structure. I'm going to upload this file, please, in the postcard file. Where is my postcard file? In Silicon 5, the postcard file. Upload. You select the format that is VASP, postcard, and calculate my structure. There it is. Okay. Look this. So this is the first Berlin song, see, of my FCC system. As I mentioned before, the calculations has to compute or when compute the energy has to compute in all the points inside of this. There are infinite number of points, right? Because a continuous space. But that's the reason Monhorsepack, what it does, it discretizes and just computes a few points here. But in these points, there are very, very important points that we call the high symmetry points, and it's here, as you can see here, right? So here you can see even the model we are using. Here where it is plotting the 2 by 2 supercells. You know, this if you put just 1 1 1 is the cell that we are using. This is the actual cell that we are computing. See? So it is everything goes looks fine and so on. Okay, so now what we're going to do is to check this. Please go here down and you see this vast k points input for this. Look this. Okay. So what we're going to do is the following, please. We're going to use, we're going to choose this, right? Here it is the file that we have to replicate. This file I created using this data here, you see? So you can copy this if you like. I can copy it copy to the keyboard, right? And after I'm going to paste here. Where I'm going to paste in this k points hyphen bs. You see, I'm going to create this file bs, and I'm going to paste it here. Okay, it's one way. Other way is like this. Do this. You can copy these k points hyphen bulk, paste it here, and I rename it like bs here. See. Now I open this in my graphical interface. See, I select everything and I copy this, copy everything from here, and I paste it here. Sorry. And I paste it here. There it is. Okay. How many is the intersection I'm asking you is 35. This is here. So basically, I will tell you how many intersections or how many divisions you do along these high symmetry points. And we're going to go from L to gamma. Okay. We're going in this path. Okay. L, gamma, X, K, and gamma again. Okay. So I'm going to copy this. I'm going to do this. I'm going from L to gamma. What is L here? See? L to gamma. I'm going to start to edit this, you see? L to gamma, see? Right? Now I put here gamma to X, where is X is here. And now X to K, what is K? Here is K. X to K, and K to gamma, and that's it. That is everything, okay? With this, I have this, Control S. I'm going to pause this here. Okay, so now we are ready to run this, please. Let's run it, okay? So we have this. Check, please, again, we'll check the key points that we're going to use. This is the key points, correct? Key points BS is there. And that's it. We're ready to run. The postcard file, we already say the postcard file is correct. Right. So will be this bulk. So this file will produce postcard key points. This file will produce many outputs. Okay, so we're going to check in a moment. So it's running, finished. Okay, so look this, ls. So we have bulk.dat. Look this, what we create here. So this is the total energy of my system, of this bulk system, okay? In a moment, we're going to discuss the cohesion energy and so on. What else? Look this, we have this charge, this file, chcar.bus. This is the electronic density, and look this, we have this procar opt. This file also, we have to understand how to plot it, okay? We're going to do it in a moment. Okay, so I'm going to wait here till everyone has this. Okay. Let's wait till everyone has this. Okay, so I'm going to close this. Okay, so we're going to start part 5, please, to analyze the data. Part 5. So let's create a section here. And I'm going to copy this, as I mentioned this, to create my, point out where is my work directory, right? It's my part 5. 5. This silicon tree. Okay, so I have this. I start with my. So the cohesion energy in electron volts for silicon FCC using PVE is predicted. How is this? So would be, the equation says is this, right? I'm going to copy this equation if you like. Right, I'm going to copy this equation. This, we need the energy of the pool. So the formula will be at the pool. This divided by n minus E the atom. See? And here I have to replace E the bulk by this value, right? E the bulk we computed already here. It is here, please. Here is the bulk. Is this value. Minus 10.2. E the atom. The atom we also computed here is atom dot that here. Here it is. Comma and n. How many? What is n? If you don't know what is n, so just check the postcard file. The postcard file says there are 2 silicon atoms, so n is 2. So the answer is this. Okay. Question is what this means. It is negative. What does it mean, please? Somebody, please. Don't forget. Don't to write down your comments. Okay, about this. Okay, now next is we are going to analyze the density of states, the Doskar file here. You see, that is the Doskar file. Very important. The density of states is one of the most among the most fundamental descriptors in any kind of system, but periodic system. Density of states only can be defined in periodic system. Crystal or everything could be periodic or can form a crystal or a solid. We can infer what would be the density of states. In a molecule of isotonic system, it's not possible to define the density of states. So basically, the density of states is a consequence of using block function, right? We are going to see this later, but this relation when you're using periodic Boolean conditions, when we are studying crystals, okay? In the isolated system, it's not possible to define the density of the states. Remember this. And in an isolated system, we only talk about the molecular orbit. Also, that's the best. Okay. So what is this, please? In this, we have a lot of information here. We have here this information here, please. This is important. This is here is giving me the range of values of energy. So if the density of state is going to be from minus 8.19 till 17. So here is this value till 17. See, you go to the last part here, 17, this value. You see? That is the range of energies. How many times how many divisions has this with project? How many divisions? 3,000 divisions, 300 divisions. We can increase more. If you want more precise, you should increase this value. We leave it by the default, it's 300. Next, this is the Fermi level. In this case, the Fermi level is defined as the highest state occupied, not the highest molecular. This is the highest state occupied, right? So in solids, we call this Fermi level. So let's say if you want to make a comparison, the hormone in molecules here will be the Fermi level. Okay. So by default, VASP put the Fermi level at the highest state occupied. So above this is that. Okay, and that's it. So in this case, in this arrangement of data, we have here the energy, the density of states, and the integration of the density of states. So this is the integral of the density of states from minus will be this in this case will be from minus. For instance, here this integration will go. This value will be the integral of density of states from this value till this value here. See, that is it. But what we are going to plot is only this column and this the first and second column. But now, since here also we're going to define the partial density of the states, you see. So the partial density of the states is going to give me what happened with each. Let's say we can project to atomic orbitals, and here we are going to have the energy. This will be the S component, in this case 3s, because the valence electrons has the 3s channel. This will be the P, Py, Pc, and Px, and this will be the D, 5 orbitals. See? So that is the reason they compose in atomic orbitals. So since we have two silicon atoms, there will be two blocks of this. As you can see here, one block, second block here. See? So right now what we're going to do is to manipulate this data to visualize this data together, okay? So let's start with this, okay? So first of all, let's call this, okay? So I'm going to call this input. I'm going to import the density of the DOSCA file. Sorry. The DOSCA file. And you please don't forget to put this like this table. Otherwise, Mathematica won't understand we are entering this as a numbers, right? Okay, so we import a whole file. So all this file is imported, right? But we need from this value, the density of states only goes from this value till here. So we are going to do, first of all, the plot of the total density of states will be from here till here, please. So how to get this, please? So this is the line here. If you like here, you can check this. Look this. Here is if you use the command bin, you can check even the values of the lines here. You see in this part here is 1.4. Look this. I'm going to take only the density of states will be from this line, that will be the seventh line, till the 7 plus 300 will be till here. Till here, please. 307. You see? So for that reason, I'm going to start with this. Okay? So I'm going to put the DOS equal to input, right? seven, from the line 7 till the 7 plus 3 halves. 6. That is the data, but I need the first and second column. So to extract the first and second, you can take this L, comma, 1. That's it. See? Now we can check this. The dos, 1. See? That is the first value of the decided states. Let's check the last line. The last line will be dos minus 1. Don't forget to save it. I'm going to pause this now. Yeah. So we have to check this, the Fermi level, please. Fermi level will be like this. Input. This value, right? Look this. I need this value. So in what line is this? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 6,4. You see? That is my Fermi level. And now we are ready to plot this. So let's plot it, okay? List plot, okay? The dos, comma. And let's put this. Join true. Okay. Access false. Frame true. Frame level. We're going to put like this. Energy, comma, dos. In what units? In states per electron volt, comma. Grid lines, here, comma. Grid lines style. Like this. Directive. Breadth. Thickness 1. Base style. Font family. Types. 18. Filling axis. Filling style. If style. So thickness. 5. Image size. Load range. All. And we're going to have this. Okay. So, okay, so let's